Hi, my name's Hamish, and today we're going to talk about fire. So, fire has always fascinated me because it's a basic phenomenon that we're all deeply familiar with, but it's also deeply strange. We all know what fire is. Fire comes from a match or a lighter. If you hold up a flame to a piece of paper, it'll catch fire. But if you stop and think about it, why should that actually happen? Isn't it kind of bizarre? There's a little bit of hot yellow gas that destroys everything it touches in a chain reaction. It sort of has this magical quality to it, like electricity. But unlike electricity, which is invisible and difficult to interact with, fire is really easy to play with. If you've ever tried building a fire, you already have an intuitive understanding of it. You know that lighting a match is easy, but lighting a log on fire can be really difficult. And even if you do get that log going, sometimes it'll go out all by itself. So what's actually happening here? I was never satisfied with the explanations I got in school, so I made this video to try and explain it to myself, and hopefully you. The first thing to understand is that fire isn't a single process. There's actually a few things happening at once. You can break down what's happening in a wood fire into 5 parts. First, the wood heats up and dries out. Next, once it gets dry enough, the wood begins to decompose into simpler, highly flammable gases and solids through a process called pyrolysis. After pyrolysis, the volatile gases released quickly begin to oxidize and burn off, followed by the solids. Last, once all the solids and gases have been oxidized, you're left with a pile of ashes, which are the fully oxidized remains of the wood. I'll explain more about each of these processes later in the video, but to get any of this to happen, you need a really strong heat source, like a match or a lighter, because steps 1 and 2 actually require you to put heat energy into the system. Once you reach the point where gases and solids start burning in steps 3 and 4, then your fire has a shot of becoming self-sustaining, because it's starting to release heat of its own, starting up the flywheel of combustion. That's why starting a fire can be hard, because you've got to clear the twin hurdles of drying and pyrolysis before it's going to start giving you any energy back. Okay, so let's go step by step, starting with the simplest part, heating and drying. This step is pretty simple. Any water lingering in the wood boils off and is released slowly as steam. You usually can't see the water leaving the log because steam is invisible until it cools and condenses. It takes a lot of energy to boil water, which means that if your wood is wet, most of the initial ignition energy is spent doing this. As steam evaporates, it even has a cooling effect on the log, like when you sweat. So until the water boils off, the wood can't get hot enough to begin pyrolysis. Once most of the water is gone, the cooling effect of evaporation diminishes, which lets the wood get really hot, just like you would if you couldn't sweat anymore. As it gets hotter and hotter, the materials in the wood can't deal with the heat and start to break down in a process called pyrolysis. In this stage, the large organic molecules in the wood, like cellulose and lignin, get ripped apart by the intense thermal energy that's building. The materials in the wood break down into volatile gases like methane and hydrogen, and carbon-rich solids like char, which is mostly elemental carbon and carbon-heavy molecules. Unlike the wood we started with, these new substances are ready to burn. Just like boiling the water, pyrolysis takes a lot of energy to accomplish, and so far, the process hasn't actually released any energy. But it's about to start with these new molecules. Once the wood is broken down, the gases oxidize first as they rush out into the atmosphere and begin to burn off immediately. The natural oxygen floating around in our air combines with the hot gases to form new fully oxidized molecules like carbon dioxide and water. Unlike all reactions that have taken place so far, which have taken heat to achieve, this is the first one that releases heat. Most of the heat thrown off by this reaction is lost to the environment, but a fraction of it ends up being absorbed by the wood, which accelerates the combustion process further. Assuming the wood soaks up enough heat to keep drying and breaking down, this is the first point where the fire is self-sustaining, and would continue if you took the ignition source away. So now the wood's actually burning, but we haven't quite described the full fire experience yet, because the oxidization of gases is a faint process which doesn't release much light at all. We haven't yet described anything that resembles the warm, yellow glow you think of as a flame. To explain the reddish-yellow color of flames, we need to look at the 4th step in this process, the combustion of the solid char, nearly pure carbon, left behind after pyrolysis. Unlike the volatile gases, carbon-rich solids burn before they melt or evaporate, undergoing solid phase combustion. Just as with the volatile gases, ambient oxygen binds to the surface of the hot char, producing steam and carbon dioxide. This is a violent process at the microscopic level, and as the char combusts, it's torn apart, pushing tiny unburnt carbon particles, or soot, into the air. The air draft from the heat pulls these sooty carbon-rich particles upwards where they mingle with any soot left over from the volatile gases combusting, and in the intense heat they begin to glow. This process of incandescence is identical to what's happening in an old-school light bulb. When you heat an object up, whether it's made of metal, as in the case of the light bulb, or carbon, as in the case of the fire, they throw off excess energy in the form of visible light. These soot particles are microscopic individually, but once they start glowing together, they emit a steady yellow glow, which we think of as a flame. So the glow is really just unburned carbon suspended in air briefly heating up to where it's hot enough to glow under its own heat. After all of this, the fire will continue until all of the solid carbon is burned up, or until it runs out of oxygen. Assuming you're burning to completion though, virtually all carbon will burn away, leaving behind just the inorganic oxidized residue of the wood. We call this material ash, and it's mostly composed of trace metals and minerals found in the wood in the form of calcium, potassium, sodium, magnesium, and phosphorus oxides. And that's basically it. What I've described so far is a very idealized process. In reality, a fire is much messier, and steps 1 through 5 are all happening at the same time in different parts of the burning log. There will be parts where the fire is burnt fully through and only ashes remain, and parts of the log will away from the flame front where there's still water trapped inside the log. Before I go, I want to touch on one point that didn't fit neatly into this explanation. What about those little blue pops of flame that you see in a fire? At first I assumed these blue flashes were really just hot pieces of soot. After all, the hotter an object gets, the more its incandescence shifts from red to blue light. However, to incandesce blue, the soot would need to be hotter than the surface of the sun, which clearly isn't the case. So what's going on? As you might have guessed, the mechanism that creates blue flames is a different physical process than the one that leads to yellow flames. Yellow flames occur due to a process called black body radiation, which relies on solid particles of soot. Blue flames, on the other hand, are a result of spectral emissions, with the blue light being thrown out by the gas itself. This is happening all throughout the fire, but in most places the yellow light of the soot glowing overwhelms your eyes, rendering the blue spectral flames invisible. Alright, and so concludes my video about fire. Hopefully you learned something. I certainly learned a ton making it. Let me know if you enjoyed it. That'd mean a lot to me. If you're thinking about making a video like this, I highly recommend trying it. It's certainly an interesting process. You'll learn a ton. So, have a great day and thanks a bunch.